Good morning, everyone. Today I will presenting on PN junction diodes, a fundamental topic in understanding semiconductor devices. This presentation will cover the formation, characteristics, and applications of PN junction diodes. N-type material is created by doping silicon with group B, five elements such as phosphorus, arsenic, and antimony. These dopants have five valence electrons, one more than silicon. This extra electron become a free carrier, increasing the conductivity of the material. The diagram has shows how the extra electrons are introduced into crystal lattice. Next one is on the other hand, p-type semiconductor material is formed by doping silicon with group 3 elements like boron, aluminum, and gallium. These elements have only 3 valence electrons, leaving behind a hole or a positive charges. These holes act as a mobile charger carrier, just like electrons in n-type materials. The figures illustrate this clearly. When the p-type and n-type materials are joined, a p-n junction is formed. At equilibrium, electrons from n side diffuse into p side and recombine with holes, forming a depletion region. This region, also called as space charge region contain immobile ions has no free carriers. The width of this region is denoted by W. The point where p and n type materials meet is called metallurgical junction. Next slide. When we apply an external voltage, the PN junction becomes biased. We can bias it either forward or reverse. The figure shows a simplified structure with metal contact and the applied voltage. If forward bias, the depletion region narrows, allowing charge carriers to cross the junction easily, and current begins to flow. The barrier potential is the minimum voltage needed to initiate this current. In reverse bias, the depletion region widens, opposing current flow. However, a very small current called as saturation current still flow due to the minority carriers flow from one type semiconductor to another type semiconductor. Properties of diode. Conductance curve is shown in figure. This curve illustrates the relationship between diode current and voltage. As the voltage increases beyond the barrier potential, the current increases rapidly. Note that in reverse bias, the current remains minimal until breakdown occurs. The Schottky equation methodology models the current voltage relationship of diode ID is equal to I as e power Vt by infinity of Vt in power of minus 1. This is shown in saturation current and then thermal voltage with the emission of coefficient depends on the temperature and the calculated by the electrons. Types of diode. PN junction diodes allow current only one direction and block it the another biased, the reverse biased. Xenon diodes are special diode that works reverse bias breakdown region. They may maintain a constant voltage, making them useful of voltage regulation applications. The xenon diode is specially made up of compared to PN junction diode. It allowing current flow from the two biased condition, forward and reverse bias condition, and also kept constant in voltage level. So it is mainly used for voltage regulation applications. And then light emitting, the diode also act as a light emitting diode. Light emit when electrons cross the depletion region and recombine with holes, realizing energy as a photons. In this methodology, the light emitting and then way of direction of illumination and high illuminated level get increased by using the diode. And then photodiodes work oppositely in LED, and they absorb light generating the current or voltage. In photoconductive mode, light increases the reverse current. Then in photovoltaic mode, the diode act like as a solar cell, generating power when exposed to light. These are the applications of PN junction diode. The formation of PN junction diode slightly changed by using this kind of applications get generated. Um, from this explanation, I conclude my presentation, the PN junction diode. Thank you for your attention. Thank you.